So, 1, 2, 3 stripes, you're out, right? In honor of opening day. Okay. Okay, first let's go ahead and kind of summarize Fridays. I want to make a connection to what we're doing today. So, here we go. First thing is on Friday, we had talked about the chi-square test homogeneity. And what we have with that is more than one group. For example, you would take, your colors of M&Ms and the colors, and you had more than one group, the peanut butter, the peanut, and the regular. And you were seeing if these rates were all happening at the same rate, if the colors were happening at the same rate. Okay. And so, the difference in our conditions were just that. Since you had multiple groups, you had to say that the groups are independent of each other. And then also, since we had multiple groups, we did not just have categories minus 1. We also had to multiply that times rows minus, or columns minus 1 for the degrees of freedom. Okay, so the added dimension changed our degrees of freedom. Okay, so then we also talked about how the computation in the calculator is much different than goodness of fit. Last Thursday we did the goodness of fit. And the chi-squared goodness of fit problems were when you had the observed in your list 1 and the expected in your list 2. All right, we just had them in a list because we were told to claim for the expected. But here, on Friday, we had more dimensions, and so we put this information in a matrix. Okay, so we had our matrix A was the observed. So here we go, matrix A was the observed. And then you run the test. Okay, and the test will automatically then so you will allow the calculator to put the expected values into your matrix B automatically. Okay. So, with all that said, though, we could compute one of the expected counts by hand, and we'll practice that here in a minute. Okay. So, again, to connect to Friday, we had cranberry juice, lactobacillus group, and then a control group, and we were wondering if they had urinary tract infection, if those 3 treatment groups had a urinary tract infection at the same rate. Okay, and so we ran a test. And this statement in blue is what we concluded on Friday when we ran the test. So that was, since the p-value was less than alpha, then we rejected that the 3 treatments create a urinary tract infection at the same rate, hence homogeneity. Okay, so that was the whole premise behind what we did on Friday. And then we took it one step further. This was the last thing that we did. And we said, if you reject the null hypothesis, this is the only time. If you reject the null hypothesis, and you do not say that that the treatments are not doing creating the UTI at the same rate, then let's see what's happening. What group is having more of an influence than the other? And what did we do in that case? What helped us to see the influence that the different groups had? The standardized residuals. Very good. And that was when we then looked down here at this standardized residuals. We computed each cell individually. Okay? Now, look here at the control residuals we have. I think I may not have mentioned this on Friday, but does it surprise you that these numbers for the control are actually the ones that are least farthest away, or least away, closest to? That'd be much better. These are the ones that are closest to 0. If these numbers are closest to 0 in the control group, what's that saying in context? The control group was what? Yeah, what's this? Since these numbers are smallest away from 0 than the other groups, what's that mean, Pierce?
They're having the least amount of effect on either side. So.
Okay, they're having the least amount of effect on the chi-squared number. but specifically them being close to 0, standardized residual of 0 means what happened? There's no change because the observed is what was expected. Okay? What was observed is what was expected. So if these numbers are close to 0, does it make sense, do you think, that the control group has the values closest to 0? Because that means they would be closest to expected. Okay? All right, so make that connection. I think in this sense, the control makes sense to be closest to expected. That's why these residuals are the numbers closest to 0. All right. Now, we talked about on Friday. Since our problem on Friday asked this part that's highlighted here, does this study provide supporting evidence for the value of cranberry juice in warding off urinary tract infections? Okay. So because of that, we then used the standardized residuals to answer that specific question. So we determined there was a significant difference, and then we used the residuals right here, this one here, to answer that question. And we could see standardized value is farthest away. So we said this in red. Yes, as you can see by the standardized residuals of negative 1.87, these studies, so I'm almost now stating verbatim what the question asked. The study does provide supporting evidence for the value of cranberry juice in warding off urinary tract infections. Okay, so done. So in summary from Friday, we wanted to see if the groups were happening at the same rate, and if we rejected that they were happening at the same rate, we found significant evidence that they're doing things at a different rate. Then compute the standardized residuals so you can look at the details of which group is affecting what the most. Okay? Alright, so now on your third page of notes, right above where you have standardized residuals, we've got this thing for today. Now, if you happen to have printed these off from the internet, then this may not have been there. Did you do that, or did you have your off? Oh, yours is there? Okay, good. All right, good. Okay, so let's talk about the last item of this chi-squared stuff. It's really very, very similar to what we've done. I mean, it's almost identical in every way to what we did on Friday. And so we want to talk about this thing called chi-squared test of independence. And that is about comparing two variables. In this first example, we're wondering, is the type of car, Asian American or European, independent of the type of driver, student or staff member? Okay, so those are my two variables. Type of car is one variable, and then type of driver is the other variable. So there's my two categorical variables that I'm comparing. All right. Now, just a question here. Of those two variables, type of driver and type of car, which one do you think is, if we found that they are connected and they are related, which one do you think is the one influencing the other? Driver or car, type of car? Type of driver or type of car is influencing the other variable? Type of car is what? So the type of car is influencing the type of driver. Okay, so that means you're saying if you drive an American car, then you are more or less likely to be a student driver versus a staff driver?
Well, if you drive a European car, you're more likely to be a staff because it's more expensive. If you're staff,
so you think if you drive a European car, then that's going to make you more likely to be a staff member? I think that if we find there's a relationship, we might be more inclined to say, if you are a staff member, that's probably what's happening first. Your status as a driver is happening first, and then that's going to influence the type of car you drive.
Well, if you're European, you're not a staff.
Okay, and so then now next, here's the next example. Good. So I would consider this kind of more of the one that's influencing. We'd be interested in these two groups, student versus staff. Okay, let's look at this next one. How about the classification of that you are on the Titanic versus your location in your floor assignment on the Titanic? So the two variables are your class versus your floor assignment. Do you consider, if we found a relationship between those where one is influencing the other, do you think that we have an indication of one that's influencing the other, which way that would go? Yeah, probably the class is going to tell you what floor you are, is going to be more of an indicator of the floor you're assigned to. I don't think the floor you're assigned to is going to then make you your particular class ticket.
Are there more floors and are there multiple floors in each deck? Or are there 3 floors total?
I think that's beyond the scope of this thing. You're missing the whole just general idea. Okay? So, I will also say one more thing before we go on. I don't think you can always determine which one is influencing the other. Sometimes the variables are just interconnected and you can't tell which one is the influencer of the other. Okay? All right. Or in, this case right here, you can't tell either way, right? I don't know. Okay? So here we have the assumptions and conditions are the same as what they were on Friday, and calculator computation is the same as Friday. So yay. Now let's do one of these problems. Here we go. If you turn to the second to last page, you will see this problem about the New York Police Department. So here we go. The table below shows the rank attained by male and female officers in the New York Police Department. Do these data indicate that men and women are equitably represented at all levels of the department? Okay. So variable-wise, what do you think we have going on? Our two variables then are, that's our first question. What are the two variables that we are interested in determining the relationship between? Gender and rank. Very good. Rank and gender in the police department. I will also mention I think this problem is ambiguous and unclear as to what you're going to be able to generalize to. Because in my mind, are you going to take this information, which is made up of 37,379 officers? Do you think you're going to take that and generalize to the New York City Police Department? Or do you think you might generalize to a broader group than that? I think because, to me, this almost sounds like the whole population of the New York City Police Department. I mean, so I'm pretty sure I'm not going to be inferring to the population if I have the population. So because of that, I kind of speculated that I'm hoping to maybe infer to a bigger population than just the New York City. So I'm kind of thinking, and this is ambiguous, so it's up for, debate, which we're not going to debate. We're just going to go with this today. But I mean, in a classroom that might not have that dictatorship, we would say that that it could be, we don't know what population we're generalizing to. I'm going to say we're going to take New York City Police Department, get that information. Hopefully it's representative of all police departments, and then speculate or infer to all police departments. Okay, let's go with that. All right, so next thing I want to ask before we get into the hypothesis statements is this. Do you remember how to get an expected value by hand without your calculator?
What?
Do you know how to get this expected value here for the male officers, what's expected to happen without using your calculator's matrix feature? Yes. Good. Good. So the way that you can get this expected value here, and I want you to go ahead and use your calculator right now and do that. You take the row total for that cell. You multiply it by the column total for that cell. And then when you are done, you divide by the entire total of all the data. So in other words, if I am interested in getting the expected for male officers, I'm going to do this 26,181, that's the row total, times 31,766, that's the column total, and then divide that result by 37,379. Okay? You're going to want to round to 1 or 2 decimal places. Not whole number, it doesn't have to be whole number. Expected is okay to not be a realistic number. It can be a part of an officer. Okay? So that comes out to be 22,249.5. Okay, so that's how you could do each cell by hand. How could we do that with the use of our calculator? Since I've got 12 cells there, and by the way, you do not need to fill in this total. Those are going to be identical to the observed matrix, so I should have just not put that on there, so my bad. But I want you to fill in the rest of those. Do you remember how to do that? First, what should we do? Okay, let's plug in our observed information into matrix A. Okay, so we're going to go, so we're going to go second matrix over to edit, hit enter, and it's a 6x2 matrix. So put the observed values into that matrix. Okay, and those are the ones that you have there on your paper. Don't include the total column. Don't include the totals. All right, so fill that in. All right, so how do I get the computer or the calculator to compute all of that expected matrix for me? Yeah, you actually have to do what? You have to run the chi-squared test. And the process of running the chi-squared test, it will come up with those expected values and paste them into matrix B. So stat, over to test, go up to chi-squared test, not the chi-square goodness of fit like we did last Thursday. And see here, I have my observed in matrix A that I put in there. You don't have to put the expected into matrix B. It'll compute that for you. So I'm going to calculate and run the test. And since I have those numbers there, go down to question D on your paper. Go down to question D since we got those things there and fill in the test statistics. Chi-squared was 290. That's huge. That's a ton of expected values out there. Chi-squareds out there. Yes.
On one of the homeworks, it was asking about a relationship between chi-square and the p-value.
Mm-hmm.
What is that? As the chi-square gets higher, what
Gets lower. Because that, as you go further out in the chi-squares, the size of the tail and the area in that tail is getting smaller. Now, look here, this p-value. Did you notice this p-value is 0? I mean, look at this. 1.32 times 10 to the negative 60th. I don't think we've even seen one ever that small this year. So that is majorly close to 0. And so then our degrees of freedom is 5. Okay. So, what we're hunting for, though, is this entire expected matrix. Where are you going to find this entire expected matrix? In matrix B. How do you best visualize matrix B? Go to it, but actually in what mode? B edit. So go over to edit, go down to B, And boom, there it is. Okay? That's what I'm saying. What is that first thing? Okay, whoop, there it is, or what? Whoop, whoop, there it is. Okay, whoop, whatever it is. There it is. See, now you guys are addicted. Every time we're saying something, then what happened? You're like starting to put a song with that phrase. It's addicting. You just start doing that. Okay. So there are your expected values. You should write them with 1 or 2 decimals. Expected values are allowed to not be realistic. So plug in all those numbers over here. And so fill in all these numbers right now on your paper. Okay. You guys got those in? All right, I'm going to get you started here on this null hypothesis, and then I'm going to let you work on this yourself, and we'll come back and meet together and see if you got everything done correctly. So, the null hypothesis of this kind of problem, of course, since it's a chi-square test of independence, we want to use this word independence, or is there a relationship between the variables? So here, the null hypothesis is that nothing is happening. Rank is independent of gender. They are not connected. And I am going to generalize to all police departments. So the rank is independent of gender for all police departments. Okay, so that's my null hypothesis. Then how would that alternative hypothesis sound? Okay, that's right. Rank is not independent. If they are not independent, they are connected. Something is happening. Gender is affecting the rank, or vice versa, whichever one you deem to be the... Okay, so I want you to do that. Rank is not independent. Now, of gender for all police departments. How many groups are we going to be referencing on this problem? Do you want to reference it detective, sergeant, lieutenant, captain, or higher ranks, or do you want to reference it as the male group and the female group? I think since, do you see this problem more as, if we find a significant difference, the male or the gender will be influencing the rank, or do you think the rank would be influencing your gender? Okay, I'm pretty sure it's going to be your gender influencing your rank, so I'm going to go with defining my groups by gender. So this first one, if I have 2 groups, my conditions better be about 2 groups. So here, look, my first one for the random is that I'm going to assume that my male and female groups of the New York Police Department are representative of the male and female groups for all police departments. Since that's what I'm intending on generalizing to, and I'm having to go with that, the New York Police Department male-female groups are representative of all police department male-female groups. Okay. So when you do independent, how's that going to look? Or less than 10% are going to be for what groups? Male and female. Totals, yes. Okay, so I'm going to pause and let you guys kind of work through the rest of this, see what kind of conclusions you can come up with. And before I let you go and do that, remember that if you end up rejecting the null hypothesis, you're going to want to go deeper and see specifically what's happening. And how would you do that? How would you get details about the different groups? Correct. With standardized residual. Okay, so if you reject, you're going to want to do that standardized residual. Okay, so I'm going to give you a few minutes to work on those. All right, let's see how you did. When you did your independent, you wanted to do the males and the females separately. Okay, so the male total of 31,766, less than 10% of all males in the police department, because that would be the population. 5,613 is less than 10% of all females in the police department, because that's our population. And don't forget this one, we have two groups. So we have to say that the groups are independent. So the male and female groups are independent of each other. Now, for large enough, it's about all expected counts being greater than 5. But you need to, quote unquote, prove to the reader where you got this information. And so that would be from this expected matrix that you had filled in up here at the top. And the lowest one I think was 34 point something, so we're good. Okay. And so then we had already determined those test statistics when we ran our test. So with that p-value, what are we going to end up doing? Rejecting. So what we end up saying is our first basic sentence with our p-value of about 0, that's less than alpha. I reject that rank and gender are independent of each other. I'm rejecting that. So there's something going on there. There's some connection. Now, I pretty much go answer the question verbatim. Okay? It's always nice to rely on and reference exactly what they ask you, because then you feel comfortable that you're answering exactly what they want. The question being this: do these data, I know we don't like that, indicate that men and women are equitably represented in all levels of the police department, or all levels of the department? So here I pretty much spit that back out. The data indicates that men and women are not represented equitably in all levels of the police departments. Okay? So that answers their specific question. And once we have that, if we end up rejecting, we want to know more information. So most likely it'll ask us, in the event that you end up rejecting, comment on what happens. So yeah, here it is. If you conclude to reject the null hypothesis, create a table for the standardized residuals. So I'm sorry, I also included total on your little table there. You don't need to have the total section. Okay? So you don't need, I know this is female. Unfortunately, these cannot be done with the calculator. I have found you actually can do just this top part. You can do observed minus expected, but you can't square root by this. You can't do the square root of expected. Although I'm going to try something and double check that, okay? So you pretty much are going to have to do those by hand. And I did that. And so then when you have those items, of course you'll be asked to comment and, and interpret something about what this says. You should always say that you, as you can see in the standardized residual table, you should make that kind of comment. You should comment on any general trend you see. And then I would also, it's always good to give a specific piece of data, so I would definitely comment on the piece of data that is most outstanding, the one that is farthest away from expected. And so here I can see that females are most grossly underrepresented in the rank of sergeant, because the standardized residuals are telling me that's the farthest one away from expected, when you compare them to each other. So here is some sentences that I wrote. So it should be something along these lines. As you can see by the standardized residuals, okay, so that's always a good thing to reference. As you can see by the standardized residuals, let's see if we can get this thing done here. There we go. Standardized residuals table. Females are underrepresented in the ranks of sergeant and higher. How did I know that? What gave me that indication? The negative. Those standardized residuals were negative. Okay. Females are most underrepresented, and then I put the specific piece of data, negative 9.14, in the rank of sergeant. Okay? I referenced where I got my data. I gave a general trend, and I gave a specific piece of data that was most outstanding. And of course, if they had asked me about a particular group, for example, on Friday they asked about the cranberry juice. Of course, if they had referenced a particular group, you would definitely want to comment on that. Okay. So now, with that being said, I want us to look at the warm-up. Okay? Let's review that this chapter, chapter 26, is about 3 tests. Chapter 26 is about chi-squared goodness of fit. For chi-squared goodness of fit, you have multiple 1 proportion z tests. They will have you compare to a claimed percent. Remember on Wednesday when you did your M&M's lab, I told you what the M&M company said that your type of M&M's proportions were. So you compared your one group to the claim. Comparing one group to the claim is a chi-square goodness of fit. And that is the way, when you did that, you put your data in list 1 and list 2. Okay. And then Friday, we did the chi-square test of homogeneity, chi-square test of independence, and those are both multiple 2 proportion z tests, or even more. And then that's when you did the matrices. Okay? All right, so I want you to take a minute and read your problem on the front of the warm-up. Just read it. Don't actually do it. Read the problem on the front and read the problem on the back, and I want you to think in your brain which test represents these. You need to be able to tell the difference between these 3 tests. So 2 of the 3 are on this warm-up. So figure that out. How about that? So on the front side, we are talking about testing appropriate hypothesis to decide if the professor's, the professor's most recent grade distribution matches the historical. So this historical grade distribution is basically the claim. So we're comparing one group of data to a claim. Therefore, you guys were right when you said this one is a chi-squared goodness of fit. So where will you end up having to compute your data? Will it go into matrices or will it go to list 1 and list 2? Okay, list 1 and list 2. So your observed is going to go in your list 1. Your expected are going to go in list 2. And I will tell you, this is a common error I've seen today. When you get this expected, this is the percent times the total, meaning total of all of the A, B, C, D's, and F's. This is not just the percent of the A's and the percent of the B's and the percent of the C's. It's the percent of the total grades that he is comparing. What would your null hypothesis be for this? It is so almost written right straight up there for you. Null hypothesis. Yeah, look at the question. It starts here. The professor's most recent grade distribution matches the historical distribution. That's the null. Okay, and the alternative is it doesn't. Okay, what is the indicator on the back on number 2 about the type of test on this one? This one is gender versus, so we got 2 variables, gender versus eating breakfast. Okay, so what type on this one? Okay, chi-squared test of independence. And what was your clue there? Yeah. Okay, it has a test of their independence, so that's pretty big clue right there. Chi-squared test of independence. And computationally, what will we be dealing with? Matrices A and matrices B. What group, if you end up finding that there is a relationship, what group is your influence? Do you think breakfast influences gender, or is gender influencing breakfast?
Breakfast.
Yeah, probably so. Okay, so your assignment is to do the phantoms model on both of these, but you know what? When you do phantoms for chi-squared, you can't do the P of the phantoms. So you're pretty much doing a phantoms without the P. Phantoms, that's right. Phantoms. Okay, so your homework is to complete the warm-up so you're prepared for the quiz tomorrow. And phantoms, there's no phantoms.